we invite you to use the chat for questions, and we will make sure that you will then either receive an answer or get the possibility to use the mic. If you use the mic, please do not hurry. We have enough time for having a good discussion without hurrying. Please make use of the survey for feedback on the agenda page, and you can comment on Twitter on our hashtag, or send feedback to the e-IRG Secretariat. Next slide, please. What is e-IRG? Well, e-IRG is working since 19 years. Next year, we will have the 20 years celebration. This will happen during the Swedish presidency. e-IRG has a vision. It's a member state body, and the vision is to facilitate integration in the area of European infrastructures and connected services within and between member states at the European level and globally. The mission is to support a coherent, innovative, and strategic European infrastructure policy making, and second, to enhance the development of convergent and sustainable infrastructure services. That's why we reflect on this vision and mission, producing papers, white papers, roadmaps. The next slide, please. Which are the translation into reality of our reflections. I'd like to remember in this context that we have produced the infrastructure commons as a document which paved somehow the way to the European Open Science Cloud. I say some way because it's just one of the cornerstones of all efforts that now led to the European Open Science Cloud. This happened in 2012 with the Infrastructure Commons for Knowledge, Innovation and Science. e-IRG stresses the need for infrastructure coordination at the national level. I remember again, we're a member state organization, and strong national building blocks, enabling coherent and efficient participation in European efforts. This was translated into a document called e-IRG Roadmap, published in 2016. And the further activity was published in 2019 with the name National Nodes, where we offered a vision on how to initiate the role of national nodes in the implementation of the infrastructure commons and the instantiation as the European Open Science Cloud. Our last paper was published last year, which is a white paper in 2021. And we are now working on the second part of this white paper. Please, next slide. And we believe that we will be able to publish it by the end of this year under the Czech presidency. The e-IRG white paper 2021 has been published at Zenodo. You have the link on this presentation. I invite you to take a look at this document. Next slide, please. That's a moment for me to say thanks, many thanks to all our colleagues and experts that have contributed to the realization of these workshops. This happened under the chair of Volker Beckmann, France, then Panos Argyrakis from Greece, Marko Bonac from Slovenia, Jan Gruntorab from the Czech Republic, and Stefan Hanslik from Austria. As e-IRG delegates, they contributed to the realization of this workshop. And they were supported by our colleagues Jan Bibelitz, Fotis Karayanis, Michael Maragakis, and since a few weeks by Bernd Sauruga here in Austria. Next slide, please. I now would like to give the floor to Volker Beckmann from the French presidency and, of course, e-IRG delegate for France. Volker, the floor is yours.
Yes, thank you, Paolo. Yes, as Laurent already explained yesterday, Laurent Crozet of our Ministry of Higher Education and Research. We have a very high priority on the green and digital transition. I think e-infrastructures can and have to play a very important role there. On the digital transition, it's kind of obvious, but also on the green transition, we have to raise awareness that we, with the e-infrastructures, we have a carbon footprint, and we have to work on this to reduce this carbon footprint in order to participate in the general approach to mildden the effects of climate change. And I think this discussion this morning will be very interesting there, because we see some highlights of what can be done, and we see some different approaches there. And I'm very much looking forward to that. Thank you.
I'd like to give the floor to Peter Wittenberg, who will be the moderator and chair of this session, the whole workshop. Peter Wittenberg is an expert, is in different roles. He has participated in first in innovative initiatives. The last one, his last endeavor, is the Fair Digital Object Forum. And he has been directing the Max Planck Computing and Data Facility for years. Peter, the floor is yours.
Yeah, thank you, Paolo, for this introduction. So I don't have to say anything about myself. That saves time. So Paolo and his colleagues asked me a few months ago whether I would like to moderate this session, and I, of course, was happy to accept, since, as Volker already indicated, the challenges ahead of us are huge. And my question is always, are we trying to square the circle when talking about this twin which you have as topic for this session? So we will see. We have, as you can see, we have 4 distinguished speakers in this panel, and then have a discussion at the end. So as Paul already said, please make comments in the chat. We'll follow the chat and raise the questions and afterwards. So each speaker has 10 minutes, and I hope you're all aware of this. And I will raise my noise after 8 minutes, probably. Then let's go. So the first speaker is Lorraine de Monterrey. I hope I pronounced pronounced it well.
Yes, that's quite well. Thank you.
Yeah. So I saw, Lorraine, that you had some relation with PricewaterhouseCoopers, but now I understand that you are an independent consultant on these issues which we are talking about. So Lorraine, the floor is yours.
Thank you very much, Peter. I will share my screen.
Yep.
So before I start, I'd like to ask everyone a riddle. What do you think is the commonality between an email and the Apollo mission? So you can discuss in the chat.
What was the last term, Lorraine? Sorry, I didn't get it. Email and?
And the Apollo mission to go on the moon.
Oh, Apollo mission. Yeah, now I see it. Well, I think you give us a too big of a, how do you say, rätsel? What's it in English? Of a question.
So I can give you the answer.
Okay.
The commonality is that the onboard computer of the Apollo mission had a storage capacity of 70 kilobytes and a RAM of 4 kilobytes, which means that currently each time we send an email, it requires more power than the computer of the Apollo mission that allowed us to go on the moon. So this is a thing to understand how digital technologies evolve today. Let me introduce myself. My name is Lorraine de Montenay. I am a member of greenIT.fr, and I am a co-author and project manager of a study, Digital Technologies in Europe, an environmental life cycle approach that was released last year in 2021. So I have a good fortune to speak first in this session today. So it is an opportunity to clearly identify together what problem we want to address when we talk about the twin green and digital transitions. So let me ask you some questions about the environmental impacts. So considering the budget that will have to be respected by Europeans to stay below 1.5 degrees of global warming, which is the planetary boundary for climate change, how many % of this budget is currently spent on digital in Europe? The answer is 40%. So this means that if we want to reduce our impact in all other sectors of activity outside of digital and neither increase nor reduce digital, we would only have 60% of the budget left for everything else: food, healthcare, travel, everything. So, but that's not all. In your opinion, at the European level, how much of Europe's sustainable budget in terms of the use of mineral and metal resources is spent by ICTs? So, well, it's 40% too. What about ecotoxicity in fresh water? Because no, digital devices and components are far from biodegradable and their manufacture is far from clean. Well, this time it's 35%. I have a last one. At the European level, do you know how much of Europe's sustainable budget in terms of the use of fossil resources is spent by ICTs? Well, this time is 26%. So the magnitude of these results raise once again the alarm. No, digital technologies are not virtual. The impacts are very real, and we can and we should measure these impacts through life cycle assessments. So to understand what it is, the life cycle assessment, it is the how to say this? It is the highest methodological standard and also the European method behind the European Product Environmental Footprint Category Rule Guidance for measuring the environmental impacts of a service or products. It takes into account the complete life cycle, meaning from cradle to grave, which is manufacturing, distribution, use until the end of life stage. The life cycle assessment must be multi-criterial, which means using a plurality of environmental indicators, such as resources use, mineral and metals, such as also resources use fossils, climate change, or ecotoxicity, as I have shown you on fresh water. For digital products, we can see 3 segments that are considered. The end user equipments, smartphones, computers, printers, etc. The network, fixed and mobile network, and data centers. Contrary to popular belief, manufacturing is the stage that has the greatest environmental impact on the life cycle, and use comes second. There is another preconceived idea. It is often said that data centers have the most impact. Although in Europe, data centers already consumes about 10% of the electricity produced in Europe, over the entire life cycle, user equipment represents almost 3/4 of the environmental impacts of digital technology at the European level. This shows how important it is to consider the scale relative to the number of users of a miscellany of products, from the smartphone to the TV, including IoT, connected objects, computers, tablets. On the other hand, mutualization, pooling, is a key. So now that you have a solid ground to understand the environmental impacts of digital technologies, how to proceed? What solutions to become both resilient and reduce the environmental impacts of new technologies? First, adopt a specific mindset, a mindset of digital sobriety and low tech and slow tech. In French, we use the word sobriété, which appeals to a notion of frugality, moderation, simplicity. This means using digital technologies with moderation without any fats. Remember, on the onboard computer of the Apollo mission, the storage capacity was of 70 kilobytes and a RAM of 4 kilobytes only. This mindset allows us to rethink, to think reliability rather than power. The challenge is not so much to make current digital technology disappear, but rather to respond to the following choice. Do we want to continue to increase the number of digital objects around us indefinitely, or do we prefer to conserve mineral reserves to manufacture critical digital tools for the future of humanity? So we are at a time of choice. However, not choosing would be a tantamount to opting for a non-all high-tech digital future, an impossible future. In the digital field, it is becoming increasingly clear that only sobriety and slow tech, in their most creative and open forms, can envision a desirable digital future for our children. So now that we have the digital sobriety mindset, what to do concretely? There are two operational tools to do so: eco-design and reuse. Eco-design is the integration of environmental aspects into environmental performance of a product throughout its whole life cycle. For reuse, at the end of a first use, a product or its components are used for the same purpose for which they were conceived. And reuse can be anticipated by eco-design. Moreover, eco-design and reuse allow to limit the digital divide at the same time as they enable to reduce the environmental impacts. Applied to infrastructure issues, it is a question of making strategic and technical choices, more broadly than technological, that make it possible to maintain the flexibility and resilience of infrastructure while inducing a more parsimonious use of equipment and promoting the reuse of the same equipment. Infrastructures have a particular role to play in that they have the power to induce uses and have enormous effects of scale. You know well the cost of the last mile. Well, on the same principle, we must take into account the importance of scale on the environmental cost of devices that arrive at the end or the near end of a chain.
Lorraine, just a short remark, right? To think of the time. Thank you.
Yes. Moreover, as well as a new road induces traffic, each new technology stack encourages a technological dependency, which contributes to congestion and accelerates material renewal instead of promoting reuse. Today, it's not about making mistakes and choosing resilience. I would like to conclude with a few examples. The resilience of Peugeot due to the shortage of semiconductors. The Peugeot returned to the old analog until the end of its career. And also another example, smart meters that are pooled. In many situations, smart meters are not systematically necessary everywhere at the same time. They can be pooled. And another example, a digital boiler for residential buildings. There is a startup named e-IRG that created a digital boiler data center that can cover up to 60% of the annual energy needs for residential buildings for the preparation of domestic hot water. So the field of possibilities is giant. Are you ready to design an ingenious, sober, and resilient future? Thank you very much.
Thanks so much, Lorraine, for this interesting talk. And you gave some excellent examples how things could be changed. Let's move on to the second speaker, since we have discussions at the end. So, Cyril, I saw that you are around. To me, it seems that Cyril is a real data scientist at EDF, and probably everyone knows EDF. At least I know EDF very well, since Cyril, we were kind of colleagues many years ago when I was joined EDF when the airport Charles de Gaulle was built. So I have some history together with you. So Cyril did a lot of simulations on dynamics and fluids and so forth. I guess you will tell us something about this. Cyril, the floor is yours.
Thank you, Mr. Chairman. Just a few words about, oops, sorry, it's not good. Okay, just a few words about EDF. EDF Group is an integrated energy company present in all areas of electricity business. We work on nuclear, renewable, and fossil production, but not only, we are activities on transmission, distribution, sale, energy efficiency, and management service. So we are the main player on the French electricity market, and we have a strong position in Europe, not only in United Kingdom, Italy, and Belgium. And we are one of the world's leading electricity companies. The aim of EDF is to be the leading electricity company and a global leader for the low carbon energy production. What is important is that in 2020, EDF made a fundamental strategy commitment by including its raison d'être in its article of association. And the raison d'être is build a zero net energy future with electricity and innovative solution to help save the planet and drive well-being and economic development. Your strategy project named CAP 2030 is based on 3 strategic priorities for building a zero net energy future. The first one is creating service and solution to help customers and region achieve carbon neutrality. The second one is leading carbon neutral electricity generation worldwide by increasing the installed capacity in renewable energy, launch new EPR program, and success of the Grand Carénage program. And we work on a small modular reactor too. And the third one is facilitating the energy transition internationally. I work for EDF R&D, and the aim of R&D are to improve the EDF group performance, to prepare the energy scenario for the future, and research for external commissioning bodies. So we have 4 strategic priorities: the development and test to improve customer knowledge, promote new usage of electricity, develop offers for cities and regions, The second strategy priorities is prepare the electrical system and network for the future. The third one is consolidate and develop the zero carbon production mixes. And the last one is support the group internationally growth by developing research partnerships. For that we have three areas of research. We work on electrical system, on the climate change, and on the digital and social transition. And we identify 6 technological targets for R&D. These targets are the small cities, the nuclear of the future initiative, the electrification of end use, the small modular reactors, the low carbon electricity power system, and the energy storage. Just some words about, sorry, I have a little problem with the screen. Some words about some contextual elements to integrate. We work on planes, and these planes have a long life. We must guarantee safety and minimize the environmental footprint for planes operating over 40 to 100 years. So it's not so easy. We are faced to a fast-changing operating condition with more competitive markets and an evolution of the environment and regulation. We are faced with new business models and services like data science, open data, artificial intelligence, blockchain, and so on. We are faced with cloud computing, smart meters, and so on. And the last one is the energy transition with the evolution of the mix. We are not working not only on nuclear, but we are on renewables too. And EDF is active on all areas of energy from the generation to trading. So it's a large spectrum of activities. Just a few words about your HPC facilities. Now we have 2 supercomputers, one named Gaia and the last one named Kronos. What is important is that the power consumption for these 2 computers is near 2 megawatts of consumptions. So the main domain for HPC application, we work on the energy production. The main domain of activities for HPC is nuclear. We work on every system on nuclear plants, but we have activities on renewable, hydraulics, thermal, like solar plants and sorry, I have and wind power. So we work on smarties, and we work on smart cities and smart grids, and we have activities on energy management and marketing too. We have some challenge for the HPC and AI. The first one is a simulation of multi-scale and multi-physics phenomena. The second one is the use of probabilistic simulation. The use of uncertainties increase the volume of data produced, and we have a lot of challenge for the pre-processing and the visualization of the results. We work on connection between HPC and reduction of models. And we have a lot of works for the connection between HPC and data science, like real-time calculation, validation and qualification of codes, and so on. We develop more than half of the code used on your HPC. We have more than 400 different codes used on HPC, and today I have more than 2,000 users of HPC calculation, computation power. And we are very interesting for the future by the quantum computers. We have some activities on this new supercomputers. So for the HPC, the energy efficiency and the energy transition, We have a global strategy. For the data center side, in 2050, EDF obtained the 5001 energy management certification, and in 2022, for the 7 years, we renew this certificate. It's not only a certificate; it's a continuous improvement of energy performance. And for that, we work on different aspects. The first one is the virtualization of IT equipment. And for the scientific contribution, it's the virtualization of licensed servers, the visualization on the VDI. We have a lot of technological upgrades with the renewal of HPC facilities, the use of GPU. We work on the optimization of cold chain. We move from cold corridors to confinement. We have some adaptation for the climate change, like the use of cold or hot water cooling. We modify the set temperature of the IT rooms, and for the decommissioning of IT equipment, we transfer HPC to another EDF company. We have some activities on the apps side. We develop a significant part of your codes, and so the eco design is taken into account for new codes when in the development side. We integrate a new technology on your codes, like NEC Aurora GPU, for the optimization of energy consumption.
Cyril, may I
yes.
just look at the watch and inform you that you should please come to an end?
Yes, it's the last side.
Okay.
On the other side, on the user side, we have a lot of activities in link with the energy transition and CAP 2030. We work on small modular reactor and so on, as I already mentioned. But we have 2 POCs, and I think it's the more interesting part of the presentation. We just start a POC with INRIA on a product named Energy Scope, and another one with the Barcelona Supercomputing Center with a product named IRG. The idea is to report energy consumption per job per study to user and to the management, to define an energy footprint per code, and to identify and to optimize usage of your codes on your HPC facilities, and reduce the consumption of node for a small extended calculation time. The idea is to decrease the power consumption and this increase a very, very small part of the time consumption. And we work too on the reduction of the number of computers potentially lost. We analyze timeout and job fails, job cancelled, and so on to convince people that it's important to decrease bad jobs. And the last one is to convince people to use to keep only use full data and not everything produced on the supercomputers. And that's all for me. Thank you. Sorry, Peter, I don't hear you. Your mic is off.
Yeah, so thanks to Cyril. Thanks also for your end. So it's really good to hear that we have one company at least that looks at all the different facets which have to do with what we are discussing here. I'm wondering, you know, how many people you need to use to look at all these, to look at all these facets and how to communicate, but that's another issue. So thanks a lot, Cyril. The next speaker is Rafael Mario Garcia. I hope I pronounce it correctly.
Yeah, perfectly.
Yeah, Rafael is working at CIEMAT, former center, as we have it also in Germany for nuclear energy, and I think you changed to energy environmental technology issues, research in these areas. And you are coordinator of the area program. So I'm curious to hear what you have to say. Your floor is yours.
Thank you so much for the introduction, Peter. I will just share my screen. Okay, so
We can see it.
Okay, so I'm just here just on behalf of IRA, and we will talk about the twin green and digital transition in infrastructure from our perspective as research organization. So IRA stands for European Energy Research Alliance, which is the largest European association for making research and performing research on the energy and the clean energy transition. It is one of the stakeholders and much as main advisors of the European Commission and the Europe. And the key point here is that IRA identified several cost-cutting activities that should be reinforced within the energy sector. In this sense, it was demonstrated that digitalization is changing the way in which research and innovation is being carried out. So it was selected as a first pilot for the development of these cross-cutting activities that are nowadays so important in terms of performing research in the frontier. In this sense, the transversal joint program Digitalization for Energy was launched in fall 2020 as a pilot, and it was consolidated and officially approved by the General Assembly in March this year. So we are now in a fully operational basis. In this sense, it counts on a strategic research and innovation agenda for the monitoring of the activities of the transversal JP. So the transversal JP program is structured under a modular basis in which the 22 IRA members can group together in different sub-programs which belong to different areas in a twofold basis. On one side, we count on a couple of specific transversal sub-programs devoted to digital activities in this sense, and nowadays, because we are aiming to grow, they are high-performance computing. The series has presented us a lot of efforts and a lot of outcomes that could be deserved from the use of high-performance computing. And a second one, sub-program devoted to data science and artificial intelligence. And we count, in order to join forces and avoid double efforts and creating synergies, with different sub-programs with interest in digitalization, which are coming from other sub-programs already belonging to IRA. In this case, we count on energy system integrations, hydropower, PIA, and nuclear materials. These two latest ones are devoted to materials. And it is our aim, as it is a modular basis, as you can see there, to include new sub-programs coming from other joint programs from IRA, and also to include specific sub-programs based on major initiatives that are underneath. So in this sense, we count on a couple of projects which are just ruling the high-performance computing sub-program, and another consolidated project which rules the data science. In this sense, they are ECO project for high-performance computing and IRA data project for data science. And as the technology evolves, and we found a lot of interest, for example, in the human-centric approach that the European Commission is fostering for the digital transition, blockchain, high-throughput computing, etc., we aim to create new sub-programs under also very, very important these consolidated efforts. This is a snapshot of the different members of our transversal JP, which encompasses several institutions all around Europe. So our key research subjects and priorities, it is to position IRA in the forefront of the digital transformation related to the energy sector, enhancing their actual relationships and networking activities with principal stakeholders. And we are now collaborating closely with the European Commission's action plan for the digitalization of the energy sector. As I have aforementioned, to create a modular transversal JP in which new sub-programs and activities can be easily and seamlessly integrated. And now we are working, starting with the application of high-performance computing, data science, and artificial intelligence methodologies to topics of interest to energies. As I have mentioned before, fostering synergies and avoiding double efforts, and deeply relying on infrastructure, but not only computing ones, because we are much aware that all the facilities that are now being sensorized or are producing new energy, they can provide energy sources and so on, will play an important role in the digitalization of the energy sector, just by performing them, by creating digital twins, by providing new solutions, etc. And of course, one of the roles of the transversal joint program is to identify opportunities in which digital solutions are needed. So in this sense, we are thinking of course in Horizon Europe, Digital Europe, but not only these framework programs. Some activities carried out as an example. We have produced a couple of white and position papers in conjunction with our partner projects. In this sense, with IRA data, we have published this paper that you can read there, Advancing Fair Metadata Standards for Low Carbon Energy Research. And jointly with ECO project, Exascale, a great opportunity for clean energy transition in Europe. And now we are working jointly with the AMPIA and Nuclear Material JMPs in a new position paper devoted to energy materials research. And it will be hopefully published after a final event to be held in November in either Brussels or Rome. We are defining that. Another activity that could be useful for the exploitation of infrastructure and a clean and digital energy transition is a questionnaire that we collected about codes, repositories, and artificial intelligence methodologies that are being exploited within IRA. And you can see just the final outcome. We just compiled 65 numerical codes, 22 data repositories, and 24 artificial intelligence data methodologies that are being exploited within IRA. Of course, this is a not complete list that could be enhanced, and we will work on updated versions of this questionnaire under a yearly basis, probably. And it counts, this document, it also counts an analysis per digital tool and also per JAME program in order to foster collaborations and common lines of research. And you can see there just the link where the final document is. Some additional examples of the exploitation of infrastructures. We count on a high-performance computing catalog of services, which is available in the ECO project website. Another example, for example, is the SIBA platform, which is very powerful for non-destructive essays, including artificial intelligence, because we also can work and, as you know, use artificial intelligence and evolutionary methods for fostering the degradation in the different infrastructures that could be included in digital twins, as you know. We are now working with a concentrating solar power JP for the proper curation of their data measure at their European ERIC. And also, for example, with energy system integration for launching the European Center of Excellence on Energy Transition Modeling, that we think that it is a cornerstone for a proper exploitation of infrastructure, not only e-infrastructure, but every kind of infrastructure. Just coming to my end, in order to be very brief, this is the website. You can see the direct link there, but probably it will be easier if you just simply Google IRA, and afterwards you just click on research and programs and then DFE. And that's all. Thank you so much for your attention, and I am open for questions after all the presentations in this panel. Thank you so much.
Yeah, thank you very much, Rafael. It seems that you have a very broad view on our digital world. So looking at HPC, but also focusing on the use of HPC, which I like very much, since this is often not counted or looked at so deeply. Well, let's move to the last speaker. That's Valentin Plougarou, sorry, Plougarou from Luxembourg. Well, it seems there's a connection between the size of the country and the size of the machines which are being installed. And you will tell us the secrets. Please, Valentin, it's your floor.
Thank you very much, Peter, and thank you everyone for attending this session. I'm very pleased to show you a bit of what we are doing and of course who we are. So this talk will focus around the Meluxina system. So the Meluxina supercomputer is a new generation machine in Europe. It's one of the network, is part of the network of machines being piloted by the Euro HPC joint undertaking. So Lux providing Luxembourg is the national supercomputing center, and we are providing the infrastructure, so the supercomputers such as Meluxina, but we also have teams with skills that help people to take advantage of such facilities. So such facilities are still very much Formula One type of equipment. So you need special skills to be able to drive them properly. So on top of having and piloting the kind of infrastructure that is needed for high-end research and industry innovation, we help industry and the researchers take advantage of such a mission, such facilities. We are located in the center of the country, in the Bissen Innovation Campus. Both our offices and the Meluxina supercomputer are there, while Meluxina is hosted in a high-end facility in the LuxConnect data center. Supercomputers are nothing new. However, what is new, it's the European focus on driving value out of these kind of facilities. So there's been a top-level mission in Europe in the past years to drive new facilities, very efficient facilities, and for running all kind of computation, and not only for traditional high-performance computing, but also for high-performance data analytics and AI workloads. And the idea is to enable a wide variety of use cases. With the why to do supercomputers, why do supercomputing, why use these kind of facilities? Well, to make it in just a few words, you want to improve your time to market if you're an industry and you want to bring some new product there. In the past years, this has also been used, supercomputers have been used for bringing, simulating COVID at all possible levels, from how this impacts population, how it impacts the human body, and so on. Supercomputing is also about doing things that you cannot do before. So it's about increasing resolution if you're doing weather modeling, if it's about tackling larger problems that you cannot do without this kind of facility. And it's also, and this is quite important for sustainability, it's also enabling you to reduce the amount of tests that you do with the live products, so to digitally simulate things. And this is reducing your carbon footprint of when you're doing a high-level manufacturing, for example, because you're simply taking all of your tests, and if your simulation is good enough, you do not need to test so much in the real world. You can simply use a digital twin of the thing that you want to see how it will behave. For society, in the end, this enables us to use things better, to find new ways of using what we already have, and also improve our products and drive new knowledge that is not possible to do without these kind of facilities. So Melusina was built up in Luxembourg to enable key sectors from smart mobility, financial services, health tech, which comprises everything from personalized medicine to life science research, the industry 4.0, to logistics and space. And all of those kind of domains have a true need not only for high performance computing, but again for data analytics, data-driven workloads, and AI. And AI is seen as a true enabler today because, well, supercomputing has some limits, and scaling it up in terms of performance and also of power usage that comes with it. You're able today to use AI techniques to gain a much better speed up than you would otherwise. So where can Melusina help what you can do with this kind of facility? So there's a lot of work that you can do in the space domain, from materials design for space applications, analytics of data collected by satellites, doing space weather forecasting for when you're launching new satellites. You can help manufacturing, as we said, so digital twins, testing prototypes in a virtual environment, doing predictive maintenance so that you can have infrastructure that lasts longer. You can even simulate the virtual factories before they're being built, and you can optimize the full production process. Around mobility, mobility aspects are quite important because delivery and supply chain is very much part of the daily life. Route optimization is actually something that is quite common for HPC, and HPC is very well suited for that. And you can optimize the route that transport companies are doing, and we can do analytics of pattern of traffic behavior and things that improve our daily life. And this is closely coupled also to smart cities, so urban planning, designing of better buildings, whole city simulations and analytics at high end. All of those things are where supercomputing really excels. The Melusina system was built to be able to take in all these kind of workloads. So it's been built on a modular architecture where the highest performance part is coming out of a GPU accelerated partition, and this has been ranked as a 10 petaflop system. And it was able to achieve also very high energy efficiency through the use of accelerators. There's other modules inside the supercomputer that are helping other kind of workloads, including a CPU-only partition that does not have accelerators, but can work or can run much more different kind of applications. There's also storage, data storage, that comprises several tiers, which enables you to accelerate several kind of workflows and workloads. And all of it is coupled in what is very specific to supercomputers in an InfiniBand fabric, which really makes a supercomputer a supercomputer. In terms of the facility, so Melusina was always imagined as a very efficient system. At the time of the construction, so an installation, and the first ranking of the system 1 year ago, it was ranked as in the Green 500 based on the performance and the energy consumption during that execution, as the first in the EU and in the European Union, as the fourth system in the world, and also was quite highly ranked in terms of absolute performance, and not only performance for heavy duty compute, but for data analytics and data-driven workloads. You have to start, when you build a supercomputer, you really have to start at the facility level. So we are hosting Melusina in a data center, which is, it's a tier 4 data center. So it's very highly resilient, redundant. It's also powered with 100% green energy from hydroelectric power sources, and it's also cooled through a cogeneration plant that is burning waste wood and generating heat and then energy out of that, and this is used to cool the data center. So at the time of the installation, also the data center was called a fully green data center. So the kind of applications, and if I have a few minutes, I would like to speak about that to show you the kind of things that you are getting on such a system. So as soon as we open the system for users, we have been running a pilot program. And part of the pilot program, there's been a lot of use cases coming from industry and from research. And if you distill them to what they're about, in automotive, we've seen a material design for next generation vehicles. So projects that have as a goal to improve fuel economy and safety. We've seen workloads around agriculture, using the space sensor data to classify crops, to forecast yields, to see how rain will impact the things, to do better food planning, to improve food security. We've also seen purely computer science workloads that will lead to enhanced artificial intelligence applications, and they will be used to boost up different kind of domains. There's been work around flood detection and doing better water management for mitigating disasters and enabling us to protect our biodiversity at a large scale. Around climate neutrality, there's been some interesting work, especially around the better use of biomass. Instead of using fossil fuel, to use biomass, which comes with very big challenges for industry. And this is something that supercomputers, where supercomputers can help. And also in particular personalized medicine, so life sciences work, they're getting a lot of benefit out of these kinds of facility, because you can use machine learning to enhance traditional simulations and build better medicine for the future. So out of all of those workloads, there are still some that are going to come. So we're going to see over the lifetime of the Melusina system a lot of different kind of use cases, and one that I'm very happy that is coming to us is a part of a European flagship project, which is called Destination Earth. And I believe in a second session today, there will be a much deeper presentation on this. And the idea there is to do a digital twin that enables us to predict the climate change, predicting extreme events and being able to drive better policies and better use at the Earth level, so being a full Earth digital twin.
Hello, Valentin.
Yes.
I'm looking again at the watch.
So this is actually my last slide. So I hope to, because this is also the last presentation, I hope that to have an interactive discussion next. So looking forward to the questions that arise, and thank you very much for your attention.
Yeah, thank you very much, Valentin. So, well, there are a couple of questions and comments in the chat, and as Paolo said, they will be answered. So we should look at some maybe and see how we can deal with some of them. So let me start with a comment which comes from Peter Brenneman. Peter, I will not read this all, but Peter looks at the consumption of these big HPC machines, and we had now a couple of presentations of HPC machines and usage of HPC. So let me start with that question. And Peter refers to LUMI, and we know that many people start putting large centers, data centers in industry in the North countries. And I've looked a bit at the LUMI stuff some time ago, and they do heating of the whole area, and have, of course, green energy to let the machine run. How would you all see this? So the HPC people, how would you see this? Shouldn't we all use the northern countries for running HPC machines? Or what is your justification to not do it? There will be certain reasons, I'm sure. So whoever wants to start. Maybe Valentin or Cyril, sorry, or
on my side, I'm seeing also another question, which is around what enabled Meluxina to be in the first in the EU in the Green 500. So I can tackle two things at once, maybe to say. So supercomputing is also always about being at the forefront of technology, right? So
that's right.
There's HPC systems at EDF, and they've been installed some time ago, and they were able to achieve some performance per watt metric. When we ranked the Meluxina, the technology that we put inside on the GPUs, on the accelerators, they were highly efficient. So we were just a bit below 27 gigaflops per watt of performance during the execution of the top. Now, LUMI is newly installed, and the technologies in LUMI are even a bit more advanced. So there's a higher efficiency in these things. Now, in the past, going from to build a supercomputer, you had maybe 100 kilowatts going all the way to 1 megawatt. 1 megawatt is a lot of power. Now, the top supercomputer in the world that was announced yesterday at IAC in Hamburg is a 40 megawatt machine, which is it's a significant, really significant scale. However, the benefit out of these machines is outweighing the not having them. So supercomputers will be built at some point. There is a true limitation in how big you can build them and the efficiency. But we've been finding in HPC innovative ways to get better use out of the facilities that are always there. So
Valentin, so you basically refer to the competition or competitiveness and see, well, we are in a very dynamic situation, and there are some compromises one has to do. Cyril, do you want to add something to this discussion?
Yes, the 5 top 100 is based on only on one technology. You can use only just the CPU or the GPU. No, we evaluate the 5 top 100 with the CPU for EDF. And we try to move from CPU to GPU for some codes to have a better flop per watt. But it's not so easy because we work for nuclear, and nuclear activities are regularly are under have a law, and it's very, very difficult to modify codes and to validate. So it's a long way to move, but we work on it.
Yeah. Anyone else from the panel who wants to act on this?
Yeah, I would like to simply mention that, as our colleagues have already said before, that we are not only moving just to these traditional codes which are being simulated, but also to data-driven simulations in which the data locality and so on will be key. And everybody knows now data will be the oil of the 21st century.
That's the point.
So we must also think of being efficient in the use of the supercomputers, also from this perspective that we are now producing a lot of data, where these data are being produced, and how we avoid also the data transfer and so on, and we can efficient in that way as well.
Yeah, thank you, Rafael. Well, let me move to the second question, which addresses a bit what Lorraine said. And I think the one point which was mentioned from, I think, Lynn also in the chat, is about which is something about numbers, which I also have. So Lorraine, you presented a number of a set of shocking numbers when I looked at the literature about this, I found a lot of different numbers, to be honest, right? And I was really confused about all these numbers. And my question to you and maybe the colleagues is, how do you say, how stable are these numbers? How sure are we about these numbers, since they have to be the basis of our argumentation, right? So could you elaborate on this? And I would also like to ask Lynn if you have some comment on this, since this is a very important point, right?
Yes, it is an important point. There is a lot of numbers in the literature, as you said. The number I showed was the numbers from the study we just made last year with Green IT and Megaoctet. They are based on an LCA, so a life cycle analysis, right, which was peer-reviewed and considered conform to the ISO methodology. So it is a robust methodology in that sense, that the LCA methodology is the most advanced methodology and the highest methodological standard for this kind of studies. And we compared the results with the planetary boundaries. The planetary boundaries, it's another methodology which is used by the Stockholm Research Center, right, and Resilience Center, excuse me. We compared the planetary boundaries applied to the Europe scale and the result we had on the Europe scale. So this is why this number seems quite shocking. It's not that it is 40% about the whole impact of Europe. It is the current impact compared to what would be a sustainable budget for each boundary.
So I found it very good that you include the life cycle, which is often in literature omitted, right? Omitted or so. And I think it's difficult to measure all these contributions. Another point is scope, right? So when I look at literature, for example, blockchain, Bitcoin stuff, right, is not included often in the numbers, although they eat as much energy as Austria or whatsoever. We know these numbers. So is the scope very well defined in your analysis?
I would say this. We have tried to have the most wide scope possible to englobe every kind of component and digital activities that were happening in Europe. So this includes all the data centers, all the network that will be fixed and mobile networks, including 2G, 3G, 4G, eventually 5G when it was happening. We englobed also all the equipment, so TVs, smartphones, computers, IoT objects also. So we tried to be as wide as possible with some limits. So I can't be certain that we include all the blockchain that is used by Europeans, because some
that's difficult.
Because this would be a worldwide scope. So we tried to have a perimeter that would be what's happening with infrastructures inside Europe. So for sure we have some of the blockchain happening, but inside Europe.
Well, I think that's a difficult thing, but since all these blockchain machines, at least 40% or 50% are somewhere else, as we know, or even more. Is someone from the panel ready to also answer about these numbers, or is Lynn ready to make a statement here, since you also looked into this?
Yeah, I'm not sure if I'm ready to make a statement. I just asked a question because generally I think it's perceived that there's around like 1 to 2%
That's
of
right.
global greenhouse gas emissions attributed to ICT. So I was surprised. I think in your report
without
you
life
said,
cycle and a couple of areas, undefined
well,
scope.
I think with life cycle, but I think you,
no,
I mean, just the use phase,
Okay.
you already said,
Yeah.
you already listed at 4% in Europe, I think, in the report, if I'm correct. So yeah, it's just I mean, I'm not ready to criticize those numbers in any ways, but I was just surprised that they're just so much larger than on the global scale and in other studies.
Let me ask Cyril. So Cyril, in IDF, I mean, it's a huge company. Do you measure anything of this and create numbers? Maybe you reported about this, then I overlooked them.
I don't know. I work for R&D, not for the whole group. So I have information about data centers and just for EDF data centers. Sorry.
I'm also looking to my colleagues, Paolo and Jan, whether there are other questions. So I should not just put questions up. Are there other questions in the chat? So I can't look always in detail what's going on. I see a couple of comments, but these can be taken up by the speakers. There was one thing from, again, Cyril, about decentralization of energy provision. I don't know whether this will change the game, but Cyril, maybe you have an answer to this.
I don't know what is under decentralization of energy provision. I don't understand the concept. I'm sorry.
Yeah.
Maybe they are referring to the way in which we are moving from a center energy production market, in which we count on large energy producers, to a decentralized market in which we rely on renewable energies, small and medium size, and how we must reordinate and rethink of the energy mix. And
we work on it. Yes, sure. We work on it's that we name smart cities and smart production, and we work on the use of electric cars for the future. It can be like a battery. So we have a lot of work on the smarties. Sure. It's very, very different that we have today, because today we have a small number of power plants with high power, and in the future we have a lot of small power production. So it's on the network we have a lot of impact. Sure.
Well, sorry if I interrupt. The question was also in terms of resilience and so on. So this large centralized not also energy provision networks, but also data networks, and also they are less resilient than smaller distributed networks, for example.
Thanks, Jan, but that doesn't touch really the ICT aspects, isn't it? So, but it's an important issue of question, of course, for the future.
For the equilibrium between demand and offer, we can use a lot of power for the future.
Yeah.
Because it's difficult to store energy.
Yep.
Even if we work on storage.
Yeah. So
Peter.
Yeah.
There are a couple of questions by Ignacio. I don't know if Ignacio would like to.
Yeah, please.
To raise them.
Thanks. I think that most of them have been, answered. I make the question to Rafa, and he answered on the chat about the focus of the backends for the codes that they were, and the other for Valentin that has also been addressed. I just to thank both of them and the rest of the speakers for the interesting talks.
Yeah. Well, we have still a few minutes. If I looking at the schedule, yes, a few minutes. So if there's no one else, then I would like to move to the usage of HPC, of the big machines, and to have a few statements from you. So data was mentioned, and we're creating more and more data. And I mean, the storage of data is not the point, but the data, if we have data, we want to process them. And we know that at this moment, when you start a data project, 80% of the data of the project time and money is spent on what we call wrangling, right? So nothing really, which is a huge inefficiency which we have to overcome. But finally, the data will be processed, and that's of course the issue where energy will be needed. Much energy will be needed. So I think you all mentioned the machine learning issue, and this is and Raphael, I think, referred to the oil, the new oil. So what I see is that at this moment, we don't really have a data market, right? So most of the data disappears somewhere in some silos, but we're working hard on the data market, which means to me that more people will become engaged in processing data. We still don't have good models. Machine learning, as you know, we still don't know how to transition, how to take models which we train somewhere and bring them over to say new conditions by remaining old models kind of stable. We still have problems to address this issue. So there's a lot. So machine learning is really a mess, running again and again the same jobs and looking for minima. So how do you all look at these things? So we have more data, more people will use machine learning and other stochastic techniques, probably only pressing the button, use some algorithm, some package which is there without knowing. So how do you see this? I mean, there's a lot of waste of energy. That's my feeling, and we will the curve of processing data will go up since we want to democratize data. So how would you see this? So Valentin, Raphael, Cyril, and Lorraine, how do you see this going?
Thank you for the easy question, Peter. So HPC is actually good at one thing. It's about training these models, right? So when people are clicking on a button and they're exploring some data set, actually they're doing the inference part. So the model is already trained and they're just moving some data through it, and the model will say, okay, this is I will classify this, or I will predict based on that. So HPC is not part of this loop. HPC is part of the training. So
yeah, I mean, that's what I mean, right? So training. I mean, we are happy about machine learning since you know, the number of a priori knowledge, or the amount of a priori knowledge we give in is almost zero, right? So we have to fit a huge number of parameters. Yeah.
So indeed, all the deep neural networks that are taking a lot of energy to train, and especially at large scale, it's just the beginning of this thing. So there will be so as with any process,
yeah,
in the beginning you do the work, then you find out how to optimize it, and in the end you have something very efficient. If we take an example of cars, and I really hate to do analogies, but in the 90s you had 2-liter cars, and what you did with a 2-liter car is not what you do with a 2-liter car today. A 2-liter car today is much more efficient than the 2-liter car of 30 years ago. It will be the same with the AI models.
Yeah. Cyril and Raphael and Lorraine, sorry, comments on this issue. So more data, more processing, democratizing data, so more people.
Well, from our perspective, we rely on a twofold basis. I just fully agree with the importance of artificial intelligence, those stochastic methods, these capabilities and possibilities that high-performance computing is bringing to us, and with the exascale. But from our perspective in IRA, as we are some kind of holistic, we are now focusing so much on the implementation of this verification of data, because otherwise this data, which is huge and which is so diverse, will not be properly exploited. And afterwards, we are much aware of how we just process this data in a way in which we'll be able to make a reality what the European Commission calls the prosumer, this producer plus consumer. So people will be able also to exploit this data accordingly. So this is a kind of different perspective, which I think complements what has been mentioned.
Yeah. Cyril, a short word, and Lorraine, a short word.
Yes, for our activities, I think that the main the deluge of data is produced by the use of uncertainties. You have a lot of probabilistic simulation, and if you if you do probabilistic simulation for CFD, for example, you have a deluge of data. So the solution is don't move data, analyze data where they are produced, and for that we have a GPU for and visualization nodes on the supercomputer. And after that, we store only analyzed data, not data produced by codes. It can be a way, but it's not sufficient. We have a lot of works like a product named Melissa to produce and a Catalyst, a plugin for ParaView to produce only 3D or 2D visualization for in the area where they are very interesting, not for the whole domain. So it can be a way, but it's sure we produce more and more data, and it's a problem for the future. And the main problem is not large data; it's a large number of small data, I think.
Yeah, you're right. I mean, yes, yeah. So you mentioned one point here. If I just say process the data where it is generated, which leads immediately to the question of IoT. Well, process data where it's generated. These are the IoT devices, right? So, but I will stop here. Lorraine, sorry, final word on this, and then we move to the next panel.
Yes, regarding machine learning, regarding artificial intelligence, machine learning is what has the most impact, environmental impact, because it's quite energy demanding. We have to think about it with a statistic mindset, because when you do statistic, you try to have the most qualified data as possible. I think one of the solutions is to take this qualified solution in mind and take this statistic mindset for artificial intelligence, because it can sober up the number, the quantity of data that is needed to have a robust learning. So this is one of the solutions. And just to have a short word about what you were saying about smart meters, IoT, there can be a large scale effect about when we do computing near each object, because it will demultiply the number of computing activities instead of doing the pooling effect of data center. So it can be not so good solution in this way.
Okay, thanks, Lorraine. Thanks to the speakers again. And I think someone will save the chat photos and so that we can take profit of all the comments and questions. So let's move ahead to so thanks again to you. And let's move ahead to our next panel. And I see that Thomas also arrived. I saw the other colleagues earlier. So Dirk is there and Lynn was there. No, we can start. So let me briefly introduce Dirk. He is professor at HDA and ETH in Zurich. And he is not in the computer science business. He is from humanities, social and political science. And I think it's very good to have an expert from the outside of the computer science to shed light on what we are discussing. So Dirk, the floor is yours.
All right, thank you very much. Actually, I have a physics background. So I come from the natural sciences. I've gone through engineering sciences, and now I'm in the social science. My talk is about sustainability, digitization, and planetary health, and how to avoid a dystopian future. We are all aware that the main problem of our world is lack of sustainability. I don't have to repeat that. And for this reason, also, we have those sustainability development goals, or Agenda 2030. And there's also perhaps a less known agenda, which is called the Planetary Health Agenda, which is also relevant to the same subjects. The question is basically how to implement those agendas. And in fact, there has been some interest, for example, of the World Economic Forum. They have created a global cybersecurity center that collects a lot of data that can be used for all sorts of things. And there's also a collaboration agreement with the United Nations. And that is towards implementation of the Agenda 2030 and also the Planetary Health Agenda. It's about digital cooperation and many other goals that they want to pursue. That sounds all very nice, but how to make use of this data if we wanted to? And a lot of talking has been about surveillance-based, data-driven, AI-controlled approach. So basically, the idea of some people is let's collect as much data as possible about this world to get as accurate as possible picture of everything, then feed that into a huge AI system that would learn the patterns and how to run the world. Ideally, it would be super intelligent. So basically figure out better solutions than humans could do. Would perhaps be able to figure out the best possible evolution of planet Earth, nature and humanity, and then implement this plan. But that would interfere largely with freedoms and human rights. And in fact, some of these implementations in the sense of a data-driven society has been on the way and controversially discussed. We all know that from the NSA revelations of Edward Snowden and the related scandals. And in fact, the idea to create a digital twin of the world is pretty old. Since many years, there's work on this by the US military and Fortune 500 companies, and one of those systems is called Sentient World. And is actually collecting data not only about the surface of planet Earth and also ecosystems, but about people, each individual person, and those digital twins of every person are really individualized with highly detailed surveillance data, as far as I know. And then the question is, how useful would that be, and how to basically make a contribution to a better world, hopefully. And some people have brought into the play of war room approach. So basically all the data would come together in a huge data center, and their strategic decisions would be taken about the world and implemented. So the question comes up, would our civilization be replaced by a militarization? And I've addressed this in a couple of talks, in particular a TEDx talk recently. And I think we need to discuss this because I believe there are a lot of issues over here. I get quite concerned when people say that our world needs to be disrupted in order to implement change. And if people start to talk about that we would have to learn to die in the Anthropocene, and then suddenly there's a lot of talking about ethical dilemmas and trolley problems and triage, and that is highly concerning because it's really about life and death of many people. And I'd like to raise the question, is it really a trolley problem? Or isn't it more a logistic and coordination problem, also a problem of fairness? And therefore, I have to point out that digital twins need ethics and quality standards. And probably altogether, we need a new approach. In particular, we need to take complexity science on board. I've been involved in a paper that is in a preprint stage about complexity science for digital twins. We are pointing out over there that digital twin approach, that means a purely surveillance and data-driven approach is not enough and would be a too materialistic approach in a sense. The usual digital twin approach tends to overemphasize the components and to oversimplify a complex system. And this can cause data-driven governance and planning to fall short. Systemic failures could result. And in particular, the volta is not a zero-sum game. These are just a few words of warning. And I'd like to point out some of the interesting learnings that we've had in the area of complex systems. One of those areas is about, for example, managing traffic. Traffic is one of the contributors to CO2 and also to other emissions that one would like to reduce. It turns out that a new approach in which the traffic flow is controlled with traffic lights rather than the other way around, a self-organized control approach, is actually superior to the classical approach of running a city from a control room. And this is quite interesting and typical for many complex systems. There's also computational complexity in figuring out potentially optimal solutions. So that can often not be done in real time. As you can see over here, all the traffic participants can benefit from this approach. So as newspapers have wrote, there's more green for all traffic participants and also more green in the sense of a better footprint on nature. So basically not only humans would benefit, but nature as well from this new self-control approach. And that can be generalized to other complex systems, in particular our economy. And therefore, I'd like to introduce a concept that we've been working on for some time that we call Finance 4. And this is about participatory sustainability. We all know that we need to turn wasteful supply chains into a circular economy where we reuse resources. But the question is how? And all attempts of regulation, perhaps over-regulation, have not been extremely effective. But we can actually learn from nature, because nature has figured out the problem. And nature is already a circular system, and so we can take a bio-inspired approach. And there is a new way of combining synergy and cybernetics, which doesn't lead to the control room-based cybersyn approach, but to synergetics. That means the science of self-organization and symbiosis. And we can now build this using the Internet of Things, but in a participatory way. I've been working on this concept for some time. A few years back, we've called that the NervousNet project. And it has been proposed by the Future ICT project and its follow-up project Future ICT 2.0. And so the idea is to map noise, CO2, and other externalities of human activities, production, consumption, and create feedbacks, multiple feedbacks. And these feedbacks can be created by multiple currencies that could be connected to measurement procedures using the Internet of Things.
Yeah, may I just say that I'm looking at the watch again? So
yeah, I'm coming to an end shortly. So doing this would introduce new forces into our economy that would drive a co-evolutionary process towards a circular and sharing economy. And so basically the approach of, can you please unmute?
Some noise.
moderator of the session can stop this. Okay. Okay, so the approach is basically that of participatory resilience, where we reach progress by participatory innovation and by co-evolution. And this is very much in line with the idea and concept of digital democracy, where we would empower civil society by digital means and combine competition with cooperation, for example, in formats such as City Olympics that would have different disciplines to improve climate, energy use, sustainability, and resilience, doing that based on a new model of globalization that we call localization, based on thinking global, but acting local and diverse, experimenting, learning from each other, and helping each other. And in fact, we've run a little Climate City Cup to illustrate the principles. In the past, we hope that would be scaled up globally to help us all to improve our situation together. So I'm finishing by saying, I believe that Destined Earth, if we go forward with this, should take a participatory, democratic, value-sensitive approach that is based also on a decentralized approach and informational self-determination. And I would really make a big change and help us to solve the problems that humanity is faced with. So let's do this together. Thank you.
Thank you very much, Dirk. That you raised a lot of topics where one can certainly discuss. One is your discussion about the digital twin. And in fact, the next speaker, Thomas Gennen, has it in the title. So Thomas is working in the European Center for Medium Range Weather Forecast. And you will tell us something about the digital twin as you use it to do simulations and probably come to optimizations. So Thomas, please.
Thank you. I hope you can see my screen. There's some artifacts in there.
Yes, I can see it. That's fine.
All right, move to the bottom. Should be okay. All right, thanks very much. Yeah, indeed, I would like to talk about Destination Earth, our planet digital twin. So first, a few words about the digital twin and what it is and why we're building it. So digital twin is basically a replication of a physical system, although you can also make digital twins of non-physical systems. In this case, we are definitely making a digital twin of a physical system, the Earth, which is in an operation mode. And what is important in digital twins is that you have continuous data flow from your system to observe the state of your system. At the same time, have a simulation model of your asset, in this case, the Earth, so that you can make predictions and can evaluate what-if scenarios. So we have, as mentioned here, a continuous simulation observation framework in place. We have tools in place to perform the monitoring of our predictions by observations. And we are developing a technical user interface to allow users to interact with the system, to ask what-if scenarios, questions, and also to test scientific theory. Now, if you look at ECMWF as a company, we are in a pretty good position to build such a digital twin, because for our numerical weather predictions, we already collect an enormous amount of data from a lot of different sensors. So we have a quite good understanding of how the Earth is behaving and what it is doing. And at the same time, we also have a very sophisticated, high fidelity numerical model of the Earth and how it is behaving, and how it will behave in the future, where we have coupled models of the ocean and the atmosphere and the Earth and the ice and so on. And on top of that, we have what we call data assimilation model, where we incorporate observational data while the simulation is running. So if you look at the bottom left on this picture, you see that what we're currently using for numerical weather prediction, where we have a lot of observations, a lot of simulation tool, and we assimilate the data while the simulation is running. that allows us to come up with a lot of very useful information about the Earth. And if we build a digital twin framework on top of that, that allows us to interact with such a model. So as an example here, you have a heat wave in Russia in 2010, where certain predictions about local effects of climate change allowed us to predict, for instance, vegetation stress, crop failure. And if you have on top of that models that can then simulate also, for instance, food prices or socioeconomical effects and the impacts of that one, you get a pretty complete understanding and picture and means to extract very valuable, actionable information from the Earth. So why do we need such a system? So the cost benefit analysis for digital twin that you always have to do in this case is pretty obvious. We understand that climate change will be very costly, not only in terms of money, which is very well known, but also in terms of human loss. And the same goes for extreme weather events, the other focus area of Destination Earth in its initial stage, where we see that for different natural disasters, there's significant human loss. So when you look at the digital twin conceptually from a little distance, you see on the right-hand side the socio-economical aspects that was also touched on by the previous speaker, where you look at health and economics and transport and food and how people interact in daily life with their surroundings. And the digital twin of the Earth is basically a method to interact in a sensible way with the Earth and to extract information from it and allow you to reason about it. And since this is also an infrastructure forum, I would also like to say a few things on interaction with that platform and interacting with other components. So as you can imagine, a digital twin is quite a complicated system, also from a technical perspective. And here you see a depiction of how the different components work together. So you have an interface platform on the left-hand side in green, where users interact with a digital twin and can ask their questions to the system to understand how the system will behave in the future, given certain scenarios that people want to follow. That will then result in a simulation being run, data being generated, and the interaction with that data and the information extraction from that data and the processing on that data will be done on a cloud stack very closely located to the HPC systems where the digital twin simulations actually run, and allows for interaction with that data as well. Now, why are we so concerned about the data and data locality and keeping the data close to where the simulation is being run? So on the left-hand side, you see a prediction of the amount of data that we think that we're going to produce every day when digital twins are in operation. And you can see that for a 5-kilometer resolution, which is not even the target resolution that we have in mind, we're going to already produce a petabyte a day. And that means that scenarios where you pull data from the system, or we have an automatic mechanism where the data is being pushed to clients, is no longer feasible, and we have to operate on the data where the data is being generated. So if you look at it in a bit more detail, we foresee that we will have a lot of infrastructure, cloud native technologies close to the HPC where the data is being generated. And we have a more central service platform where the information flow is facilitated between these systems and the end user, which obviously is a lot less data. On the last slide, looking at the time, so it's more on where we see funding opportunities for consortia. So for Destination Earth, we're going to outsource a lot of the activities. So we're actually going to procure, we are in the final stage of procuring digital twin for extreme weather events. And we're also procuring a digital twin for climate adaptation. As part of those digital twins, there will be use cases defined for specific subtopics. But we will also explicitly create a tender for use cases ourselves, next to the use cases that will be part of these of these tender digital twins. And there we're going to really focus on novel workflows and demonstrating novel ideas on how to interact with digital twins and how to use the information the digital twin is producing in new ways. And that was what I wanted to share with you. Thank you.
Thank you very much, Thomas. Pretty much in time. And well, you also raised a lot of questions here, but we will shift up to the discussion. So let me introduce then the next speaker, which is Lynn Kark. We heard Lynn already. Lynn is assistant professor at the Hertie School, and as I've seen, also active with data processing in the area of climate and energy. So Lynn, the floor is yours. Curious what you will say, especially about your one side public relations or public policy parts. Please.
Thank you so much. Yeah, exactly. So I should share the screen first, I think. I had it on full screen. Okay. So is this good?
Yeah.
Okay.
Yes. Looks good. Excellent.
Yeah, thanks for the introduction. And as you said, I'm mostly a policy person. So I work at Hertie School and I work on climate mitigation policy with a focus on the energy sector, but I also have a background in physics and machine learning. So I'm trying in my research to combine machine learning with climate change mitigation policy. And in this talk, I wanted to talk about AI and climate change and how they relate to one another more generally, which is something that I've worked on extensively over the past years. And those two topics, generally, we can think of them as in three different ways. So AI can be applied to help with climate change mitigation and adaptation. It can be applied in ways that actually increase emissions and vulnerabilities. And then there's this third aspect that AI also, and we heard about this earlier, machine learning in particular has a compute-related footprint. And I wanted to speak about this first part of how we can apply AI to address climate change in a little bit more detail. This is actually quite a laundry list of different application areas. It comes from a paper that I've written together with a number of colleagues about 3 years ago. And we found these overarching ways that machine learning can be used to address climate change. And I'm just quickly going to walk you through these. So machine learning can help with improving forecasting, and that's something that helps the energy sector, for example, with integrating renewable energy. It can help in transportation systems, but also in forecasting extreme events. Then machine learning and AI more generally can also be used for improving operational efficiency. So ideally reducing energy consumption or resource consumption in systems such as heating and cooling systems. Freight, again, the transportation sector here plays a big role, or even reducing food waste. Something where machine learning is already quite widely used is predictive maintenance. And many companies are looking towards reducing their maintenance cost and making their systems more reliable with AI and machine learning. And if this is applied to low carbon industries such as railways, this can actually help with decarbonizing the energy sector, transportation sector. And a quite different application is in the area of experimentation and scientific research, where a lot of new energy technologies are still on a very early development stage, or they are reliant on continuous improvements. And machine learning can actually be used to accelerate experimentation and find better batteries faster and cheaper. And it also helps with identifying new clean energy materials, such as solar perovskites, for example, to improve solar energy. Then machine learning is also integrated with large-scale simulations and can speed up those simulations and make them more detailed, which is used in climate science, but also in the energy sector. And there are also applications, for example, to city planning. where people use these techniques. And a last point is on gathering information. So machine learning can analyze data sets that previously weren't as easily analyzed manually, and can deduct decision relevant and policy relevant information from these data sets. And with that, one can monitor greenhouse gas emissions, one can monitor deforestation remotely, or create new infrastructure data sets. And I wanted to introduce a few examples because this is fairly close to my research. So for example, in fall, there was the first study published that looked at larger solar PV installations around the globe, and they used satellite images of the entire world to create a data set of where solar systems are installed. And this is data that previously did not exist. And it can help for monitoring the development, but also for local grid management and policy advice. And you'd be surprised that many countries actually don't collect this type of data. Machine learning here obviously helps with computer vision approaches to automatically segment images and classify where you find solar PV. An example from my own research is this study where we used machine learning to automatically analyze text. In this case, we were interested in how companies talk about climate-related risks, so both to a changing climate, but also to transitions required to address climate change. And we trained an algorithm on our own labeled data. And with that, we were able to analyze several thousands of reports that previously manually you could not analyze, and observe trends on a larger scale, such as this shown in this plot, where we can see that actually the number of mentions per report of climate risk is drastically increasing. So coming back to the bigger picture, I wanted to quickly touch on this compute-related emissions point. I actually excluded it from my presentation, but I put back the slide back in since this came up in the previous sessions as well. And I wanted to just give you an overview of how to think about the emissions, compute-related emissions from machine learning. And this is from a forthcoming paper where we introduced a number of different frameworks on the impact assessment of machine learning. And as you see, here is the number of the ICT sector causing around 1.4% of global greenhouse gas emissions. As we know, these numbers are very uncertain, and that's why it's important to also have these kind of discussions. In either case, AI or machine learning more generally contributes to a smaller fraction of these emissions. You can contain it somewhat by understanding how much of these emissions are due to data centers, and how much of these are, for example, to cloud and hyperscale data centers. So to try to understand like what are the typical infrastructures that machine learning can run on, and how much do they contribute to the greenhouse gas emissions. The problem is we don't have better data on how many jobs actually run on data centers that are attributable to machine learning. What we also show here is what is described in this use phase box is that the different phases of developing and using a machine learning algorithm differ drastically in the energy consumption. And the most energy intensive phase is this development phase where algorithms and architectures are being developed. And here, these are numbers that one often sees, and they're very large, but one has to realize that this is rather infrequently done and by few stakeholders, whereas inference, when you use the algorithm, in and itself often doesn't come with a large energy consumption, but due to this frequent use of some algorithms, like billion times a day, actually the energy used for that phase adds up quite a bit. And in many applications, inference is the bigger energy problem with respect to the different phases. So overall, I don't know how I'm doing in time, but this is a framework that we introduced in the same forthcoming paper, where we relate these different emissions effects. And what this shows is essentially there are compute-related impacts that I just talked about. there are these application impacts, and I talked about the impacts that can reduce greenhouse gas emissions. But of course, you can also apply machine learning in ways that can actually increase emissions. And then lastly, we distinguish the system level impacts resulting from applications that can have potentially much larger effects, but are really uncertain. So this is how machine learning and AI can affect how technologies are being used, how they affect consumer behavior, rebounds effect, and so on. Am I out of time?
Well, then still 1 minute to go.
Okay, good.
You're good in time.
So we also published a report, or together with colleagues, I published a report for the Global Partnership on AI, where we illustrate what kind of policy approaches there are to help machine learning and AI be or align with climate strategies, climate policies. And in particular, here we focused on how can you foster those applications that actually help addressing climate change by better data and digital infrastructure, by dedicated research and innovation funding, or by helping those algorithms be deployed with real-world systems. But we also address the larger part of reducing AI's negative impacts more generally. And all of these approaches, of course, have to do very centrally with concepts of responsible AI. They have to do a lot with skill building, getting the right people in the right sectors, but also with international collaboration, since it's a global technology and a global problem, and we need better impact assessment. I'm also a chair and a co-founder of an organization that is dedicated to bringing together the machine learning community and those people who work on climate change problems. And we have a very active community. We have regular workshops. We're present at the COP. We have a grants program, an upcoming summer school, and we also have monthly webinars and newsletters. So if you're interested in learning more about different application areas, feel free to check out the website. We have a huge number of videos of past talks as well. So if you're interested in learning more, this might be a valuable resource for you.
Great. Thanks, Lynn. After this bit of PR, which is allowed, we return to the issues. Well, let me first say I'm surprised, or maybe also not surprised, that there are hardly no chat comments. Maybe everyone went to dinner or lunch already. There are hardly any chat comments. Are we still some people around? 34. So there's hardly any chat, which indicates that it's much more easy to discuss about HPC. Obviously, that's we can look at it, we can grab it. Much more is easy than to talk about all the aspects which Dirk raised, and the digital twin which Thomas raised, and the simulation which Lynn raised. But nevertheless, let me motivate you all to make comments in the chat. If there are no, I will just start with some questions. There is Paolo. Paolo, you raised the hand, please.
Yes, thank you very much. I'm just addressing now what you have said, Peter, concerning the chat and maybe missing of questions there. I believe that there are a lot of questions in our heads. We have still to formulate these, because all contribution of this second session, they are presenting a way of reflections which is somehow displacing our mind. So it's the introduction of new terms and new settings is forcing us to reflect on what is happening. So, for example, what does it mean for me, for myself, to reflect on the impact of the Anthropocene? Just the idea to have this point of view changes everything. Or to link ethics and philosophy to the digital twin efforts. To link ethics and philosophy, it means to change completely the differences. So leaving aside the business-like approach, then to reflect on digital democracy, for example. What does it mean to introduce digital democracy at all levels of society, not only at schools, but also at the decision-making process, to all the people who are in a status of deficiency of literacy in digital issues, I will say like this. So this is maybe the reason I have a lot of questions which are still in the mind. So thank you very much for the contributions.
Pull them out of your mind, please, in the next minutes. So I think you carried on with reflections. Maybe Dirk or Thomas or Lynn want to respond to what you said already.
Yeah, I think this is very important. We need to think about the role of democracy in the digital age and how digital technology can help us strengthen the most valuable parts of our society. And now I think there's a new process of reflection going on recently, because in the first years of the digital revolution, there was pretty much a data-driven approach, and the hope that AI would fix it all kind of automatically, you know, it would just learn everything. And
we're still in that phase, Dirk, I guess.
Well, but also we've learned quite a bit about limitations of this approach and what can go wrong and what can be improved. And so we have moved from data analytics to data science, and we're moving from this approach towards a more participatory approach. We have learned that ethics is important. There is a reflection on how to get ethics into digital platforms and technology. There is talking about a value-sensitive design approach. And so there is quite a bit of progress that shows us how to make better use of digital technologies. And I would even say we're going to enter a digitization 2.0, a second phase of the digitization, where we see maturation based on the experiences that have been made in the United States, in China, and in other places of the world. And it seems like Europe is trying to find its own place and its own approach, very much oriented at the values of our constitution. And I think this is very promising, but it needs to be worked out. And I do think we're, in fact, more or less at the beginning of that phase of the process.
Thanks, Dirk. That leads me to Thomas. Thomas, is the term digital twin, isn't that too big or so? So for me, it's still modeling, selecting some parameters, some aspects of what you can do, and we are far away from a digital twin, which, for example, takes into account the dimensions Dirk and Paolo raised. So what is different for your digital twin with what we call model?
I think your ambition level has to be indeed realistic, right? So we're not going to build a digital twin of everything. That is a concept that I think we're pretty far away from. So we're going to focus on a subset of the system, like what you also do in industry, right? So you're not making a digital twin of everything. You focus on a specific, basically you build a twin for the questions that you want to have answered.
Exactly, that's what I understand. Yeah.
So we start with two digital twins, one for extreme weather, because we know that there are a lot of people who are interested in understanding how extreme events will evolve and how we can predict them and how we can get early warnings and how we can sort of interact with them with the model to understand how we can potentially mitigate the effects or maybe even have an impact on it, right? And for climate, it's the same, right? So you focus first on, okay, what kind of answers do I want to have answered? Can I build a system that can provide me the information that I need to make decisions? And then you build it. So we're actually in that last stage, right? And we're quite humble. So it sounds big, right? Destination Earth, digital twin of the Earth, but we know our limitations.
So, and Lynn, I mean, you heard some criticism or not criticism, questions about machine learning, right? And we know that there are some aspects which we have to be aware about when doing machine learning, training big models with big data. There can happen a lot of things, and we don't know exactly what the small beasts are doing. So do you have any response to that?
Well, that's a all-encompassing question. I mean, yeah, there are many issues with machine learning, as there are with almost all techniques. And I think it's really important to start moving away from a paradigm where most of the machine learning researchers were focusing on beating benchmarks. So on standardized data sets, trying to improve the performance of very standardized tasks. And now the community, and also driven by external pressure, I think, and application pressure also, is trying to move towards creating new data sets, new specific problems, trying to see how do actually our models perform on these more application focused specific tasks. How do we deal with a number of the issues that, you know, can be summarized under responsible AI? And so I think there is a paradigm shift, but we have to move to that faster. And I think there will also be a reality check for machine learning and trying to understand how does that work in the real world.
Basically, what you say, and I know this from my last PhD, which I supported. Basically, the art is, you know, getting the right data together, but that has implication, which Dirk, for example, raised. What is the right data? Right? I mean, so there. This has already the basic question in it. You know, with choosing certain data, you can come to some minima. That's what these algorithms do, and then come to some conclusion. That's very dangerous, isn't it?
Certainly. I mean, that's data analysis, is data-driven statistics. That's right. I mean, if you don't realize that, then yeah, you should be careful using it. But there are techniques to deal with that and ways to validate your own work.
Yeah. Before I turn to Dirk, I see Paolo raised his hand. Please, Paolo.
Thank you again.
I'm
referring now to the digital twin discussions and the subset that could be created. So the convergence of knowledge from different disciplines, it's really relevant for this session of this workshop. And I would like to add another element, a further element. This is the fractals mathematical model of Mandelbrot. So the fractals theory. The digital twin of the Earth it was the point, but we can also create subsets like digital twins of processes or institutions. And if we look at them and then we apply the mathematical model of the fractals theory, then we could recognize some common elements, which if you filter them in form of data, then you can receive at the end a lot of data sets according to the theory of the fractals, and then go upstairs to the bigger model, which is the global digital twin. This is, for example, an example of convergence of knowledge.
Yep. So we already lost Thomas, and I see that Dirk also will go at 12:10, which leaves us 2 minutes. I think that's fair enough. Paolo, you certainly want to make some wrap-up statements. I would like to raise one issue, and I would like to continue this discussion, which is I mean, endless discussion. I would like to share one thing, and it's a bit of PR, Paolo. I hope it's allowed. So I told you, Paolo said that I'm in the FDO forum, and the FDO forum basically is about fair digital objects, so making things fair and having an implementation for fairness. So it's a lot about raising efficiency when dealing with data. So we will have our first conference on fair digital objects in October in Leiden. So I put the link into the chat. I would also and indeed then invite you all to come to this conference and contribute. Paulo, back to you. Thank you very much to the speakers, by the way. Yeah.
Thank you very much, Peter. I'll be short in my conclusions because you did a wonderful moderation and you made also, you offered wonderful wrap-ups. I don't want to add water to this lake of sentences, good sentences you have offered. I'd like to thank first of all you, Peter, for the moderation, then Lorraine de Montenay, Green IT France, Cyril Baudry, Électricité de France, Rafael Mayo García, CIEMAT, Centro Investigaciones Energéticas, Medioambientales y Tecnológicas, Valentin Plugaru, Lux Provide, which is the Luxembourg EuroHPC hosting entity for the Meluxina supercomputer, then Dirk Helbing, Computer Science Department, ETH Zurich, Thomas Jean, European Center for Medium Range Weather Forecast, Lynn Kaag, Hertie Schools of Economics. And I would like to state that as a next session, we will have the next session at 14 hours, up to 16 hours this afternoon. This session will be about cross-infrastructure collaboration coordination. So stay on tune, because this all is linked in according to our grammar, to what has been said yesterday. So the data space we are opening in Europe through the European Open Science Cloud. It's linked to the cross-infrastructure collaboration coordination. And of course, to what we have sent now with the twin transition, to the two twins, green transition and the resilience of infrastructures. We, as e-IRG, we will have our delegates meeting the 7th and 8th of June. It's a closed delegate meeting. We will discuss, reflect on the findings of your contributions, and also on the formula we have chosen in order to understand on how to convey the main messages of these three workshops into our next white paper. As I mentioned, we are working on it. I'd like to remind that the slides are available on the Indico agenda page, all slides. Recordings will be published on the e-IRG webpage. And further questions and comments, please let us know what you think, what are your reflections on how you could provide further inputs to the common work, because this is a common endeavor. And you can also give a feedback through a SurveyMonkey. See the link in the chat. I'd like also to close this session with the last acknowledgement. The e-IRG workshop is organized within the framework of the French presidency. So a big thank to all colleagues of France who have contributed for the realization of these workshops, and also for the realization of the upcoming meeting, the 7th and 8th of June. Then a big thank also to the colleagues of the e-IRG support project, which has, by the way, received funding from the European Union's Horizon Europe Research and Innovation Program. So thank you very much. We start now with the lunch break, and we see each other at a few minutes up to 2. Thank you very much. Goodbye from Vienna.
Okay. Thanks, Paulo. Ciao.
Thank you. Bye.
Bye.
Thank you. Bye bye.